Proving the Riemann hypothesis true is the same as proving there is a distribution pattern amongst prime numbers. Amongst primes. Proving the Riemann hypothesis false is the same as proving there is no distribution pattern amongst primes. The sieve of Eratosthenes proves by counting alone we can find all primes. If we omit all even numbers, does the statement hold true? Exceptions are 1 and 2. 1 is for some other reason, because we got to omit 1, but 2 is a prime. So 3, 5, 7, 9, 11, 13, 15, 17, 18, 21, 23, 25. So as you see, doing it by, I'm just counting by 3, 1, 2, 3, 1, 2, 3, 2, 3. And if we do it with 5s, 7, 9, 11, 13, 15. See, every fifth number will be divisible by 5. And then do it with 7, 6 numbers that aren't divisible by 7 while one number is. So, and then you can keep doing it with 9, 11, 10. Yes, the statement is true, but my hypothesis is it works the same with numbers in base 10, only ending with the same number: 3, 13, 23, 33, 43, 53, 63. All these numbers are divisible by 3. 7, 17, 27, 37, 47, 57, 67, 77. See, the statement is true. But how does this help? Well, numbers ending in 3 aren't only divisible by 3. Numbers 33 is divisible by 7, equaling 19. So, where is the earliest a number ending in 3 divisible by 7? Well, it's 7 times 9 equals 63. So what is the earliest way for a number ending in 9 able to become 3? The answer is 7. Primes can end in 1, 3, 7, or 9, except 2 and 5. 1 times 1 equals 1, and then there's all that about the different pattern organization. And what does the prime number patterns in base 10? Firstly, why does the pattern seem random? Well, it's because it is constantly evolving pattern. Every prime sets off a chain reaction that will never allow bigger numbers to be prime. At the same time, this reaction allows twin primes to be possible. 11 and 3 can only be twin primes because 12 is divisible by 3. between each twin prime, the number separating them is divisible by 3. Also, the number 15 is important because twin primes are also possible every 15 intervals. The twin primes themselves will tell us which numbers are divisible by what. The twins ending in 1 and 3 tell us the number ending in 5 after them is divisible by 15. Twins ending in 7 and 9 tell us the number before them ending in 5 is divisible by 15. Twins ending in 9 and 1, the number in between them ending in 0 is divisible by 15. But they say proof is in the pudding. The proof of infinite primes is Q equals P1 times P2 times P3 P20 plus / minus 1 is prime. 3 times 5 equals 15. 15 times 2 equals 30. 30 times P plus or minus 1 is prime, but 30 times a number plus or minus 1 is also prime, as for 15 times odd numbers plus or minus 2 is also finding primes, as well as 15 times odd number plus or minus 4. N equals any given number, or O equals odd numbers. That's why my theorem was better written out. It took me a while to figure it out. What does this tell us? It tells all given spots where twin primes can exist. 15 times 0 plus or minus 2. 15 times odd plus or minus 4. All these spots can only have are the only possible existences for twin primes that end in 1, 3, or 7, 9. And because of primes such as 7, these twin primes alternate. Example, 7 times 7 is 49. 45 is divisible by 15. So twin primes are 41, 43, 30 times a number plus or minus 1. Twin primes ending in 9 or 1 are only possible at this spot. This tells us twin primes ending in 9 on 1 will be more than 1, 3, or 7, 9, since it won't alternate with them. This also shows us spots for twin primes are infinite. If the twin primes are infinite. So the twin prime conjecture it shows that the spots for twin primes are infinite. So the twin prime conjecture is not a lost cause. This not only answers questions about primes, it also shows us primes have definite pattern. This pattern revolves around this pattern revolves around twin primes in base 10, but not the only pattern. The next pattern does not rely on twin primes, and that's when I was talking about the 3 and stuff. Like, for example, this one I did 1s. The circled spots are where primes are at, and I could do this by hand. I could do it from scratch. And this is a page that's -2, -4. So that means this row right here, 21, minus 2 is 19, minus 4 is 17. So this is a row that is above a set of twin primes, or where a set of twin primes should be. This one is plus 2 plus 4, and it's 9, 3, 7, because 11 is plus 2, 13 is plus 4. And then this one is plus 2 plus 4. It's 7s. 27 plus 2 plus 4 is 29 and 31. And that's what that up there means. This one is minus 2 minus 4. And right here. Wait, no, that can't be right. Because that'd be. No, yeah, that's right. It'd be 31 and 29. But now that you've seen that, one thing I forgot to go over is these numbers right here are just me listing out 19 times 1 because of this will be 19, 209, 309, 589, 779, 969, and I only did up to the 1,000 spot. After I got to 1,000, I quit because I don't want to go up to 10,000, 20,000, but some of them just jump arbitrarily times 1, and then it's adding 890 because of the B equaling prime times 10. So that's 89 plus 890 is 979 plus 890 comes out to that. That's the reason for the B10. It tells me where the numbers are going to jump to. So this is why I wrote this out, is because it's much easier to see. This highlighted row is a row that's divided by 3. The highlighted rows are divisible by 3. That means primes are only in these 2 rows. But only these 2 rows. And with the whole part of 1 over 3, you need 3 doors. 1 door, 2 door, 3 doors. 1 door isn't prime, while 2 doors are possibly prime. So, and then all those rows break down as such as 3, 33, 63, 93, when divisible by 3 will be 1, 11, 21, 31, and you see how it goes 1, 11. So it breaks down into the pattern I was talking about in base 10, but every third one, 7, but now from here, 1, 2, 3, 4, 5, 6, 7. This number is divisible by 7, which is 13. 1, 2, 3, 4, 5, 6, 7. This one's divisible by 7, which is 23, 13, 23, so on and so forth. And here, 27, it does the same thing, where it breaks down into 3 divisible by 1, 33 divisible by 1, 11, 21, 3, 13, 23, 33, 9, 19, 29, 39, 49, 59, 69. Seven, 17, 27, 9, 19, 29, 39, 3, 13, 23. So you you it's easy to see the pattern, and that's why. But the reason for these things is just because of the real part of 1/2, which is just 3 spots. Right now, what I'm trying to show you is the numbers that aren't. Okay, right here. So you see how this is 7, 77, 21, and then I'm missing out the 5s because we know all 5s are divisible by 5. That's the only reason this has only got 4 rows. So 7, 77, this is where twin prime should be. And then here's where twin prime should be. So let's see if it follows the 1-2 ratio. 1, 2, bang, where a prime should be but isn't. 1, but there's one more right here, the 55, so that's where a prime shouldn't be. 1, 2, and that's a 1 and 3 patterns that it's not. And then because we're missing the 5s, we're not seeing exactly. There's spots here that don't have a purple spot, but as you go down the number line itself, just this row is 1, bang, bang. These 2 spots are where twin prime should be but aren't. This one is where a twin prime should never be. This isn't, 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 isn't. Well, twin prime shouldn't be here, but it's, so it won't be, that isn't where twin prime is. It isn't, is where twin prime isn't, or where it should be, isn't, 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 should be, but it follows the 2-1 ratio. And the importance of this in the next pages will be more relevant in a second. Here's that X means it was I made a mistake. So twin prime should be here, and it is, but that's not really the beginning of the pattern. That's just beginning of this number set. So isn't, should be, shouldn't be, should be. And the reason this is important is because let's take back the 7s. The 7s are here, 77, 77. So where's the next time they line up? 847. 847, you see? So because 7 ends up, or 11 ends up lining up at 7 down. 1, 2, 3, 4, 5, 6, 7. And for on here, this is where 11 hits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that means they both start off, or start there. That means you can start mapping out which ones aren't twin primes and stuff, and you can do the same thing on here. I'm just not doing it right this second. But the reason I stop at 17 is because mathematicians have proven that there's an infinite gap of 16. So if we can map out how these numbers line up, like how this is 47 isn't going to be 847 isn't where these are. I want a spot where all these line up. So I go down. What number is divisible by 7? 35. Here's a number divisible by 7 because it becomes 50. 35 divided by 5 is 71. But 1, 2, 3, 4, 5, 6, 7. 180. 887 is where this lines up. That's 11. That number is divisible by 11, but we want 1, 2, 3, 4, 5. 1, 2, 3, 4, 6, 7. That number is divisible by 7. This one's divisible by 11. We're wanting a spot where they line up. And I don't know if I did the math on this one or in that notebook. I think I might have worked on it in here. Okay, well, I guess I'm gonna have to do the math. So 7 times 11 equals 77. 77 times 13 equals 7 or 1 or 231 and 0.077 equals 110. 401. 401 times 17 equals 7028 plus 0104 equals 7186. Now 6817. But before that, before I did the times 7, 401. 1 second. 7, 10 equals 70. 70 plus 7. So 7 times 11 equals 77. 77 times 10 equals 77. 70 plus 77 equals a number that's divisible by 77. This number is divisible by 13, 7, and 11. So to change it into another number would be 1203. I wish I had the other math paper that I worked on. So would be 847, but I want 847 to transfer to something over to the 13s. So that means for that number to be divisible by 13, all I have to do is times by 10 and add itself. No, that just makes it a number that keeps adding itself. I want that to transfer to 13. So I want 77 to transfer over, because that's divisible by 11 and 12. So 77 times 13 is 401. But 401 isn't divisible by 13. .401 is divisible by 13, but it's it's not 401, it's 501. But then that still skips. I'm half asleep right now. I gotta find my work. So times 7. 1, 2, 3, 4, 5, 6, 7 is 7. It's 1 plus 2 is 91. So 91 is where it's divisible by 7 and 13. So to jump that is 910. So that makes 2,000. to do that, to jump that. 1, 2, 3, 4, 5, 6, 7, and 1001 divided by 11 equals 999 191. So it's just 7. So that is divisible by 11, 7, and 13. And then once we know where that, now that we know where that number is, 0, 1 plus 0, 1, 0, 0, 1 equals 1011 or 11011, and that number is divisible by 13, 11, 7. Those are the three numbers that's divisible by. It'll equal other numbers as you divide. But now I want to transfer that over to here, which is going to be 1, 2, 3, 4, 5, 6, 7. So this is divisible by 7, which is 33. Now 1, 2, 3, 4, 5, 6, 7, which is 1, 2, 3, 4, 5, 6, 7. That isn't divisible by, but is this divisible by 7? Yeah, 33. 170. 170. Well, I'm going up this just to double check it because it's going up by 5, 7. The first one, ignore the ones. It's going 5, 22.